chance to speak about my recent work at KAIST. Okay, so as I gave a talk last year, this Siegel series is defined to be the local factor of a certain Fourier coefficient of certain Siegel modular forms. And this is actually very crucial ingredient in Kudar's program to match it with certain intersection multiplicity on Shimura varieties. So this talk consists of two parts. So in the first part, I will explain motivation of this work. After that, I will explain a precise reformulation of the Siegel series. So this first part is just motivation. So I will explain this very roughly. Okay. So this is motivation. I think I have no reason to use this word. Let me direct start with motivation. The motivation of this work is in modularity theorem. So let me first remind you what modularity theorem is. So let me start with elliptic curve. E is elliptic curve defined over Q of conductor N. Okay. Then we can define certain L function associated to this elliptic curve E. So we can define certain L function. This is actually called Hasse-Weil L function. So we usually write it as the following, and its definition is the following. This is defined as the product of certain local factor for all finite places, and each local factor is denoted by this. So to define this, I only need to say what this is. So this, if P does not divide N, it means for almost all prime numbers, then this local factor is nothing but 1 minus P plus 1 minus the order of the special 5 of this elliptic curve. Oh, I need more place. P to the minus S plus P times P to the minus 2S. Okay, if P does not divide N, and if P divide N, then 1 minus AP times P to the minus S. Here, AP is negative 1 or 0 or 1. So there is a technical condition to determine the precise value of AP. So anyway, then Hasse-Weil L function is defined like this.
What is C? 1 minus CP?
1 minus, yes, so this is parenthesis. Sorry. Yeah, from this to this. Yeah, so P plus 1. Yeah, this is the definition of Hasse-Weil L function. So this looks like Riemann zeta function, and actually Lagrange wanted to call certain series as L function if it satisfies several conditions, 4 conditions basically. First condition is that the series should converge on the half plane. So this is the case. And the second condition is that it should satisfy functional equation. Oh, sorry. So that it has Merowith continuation to the whole complex plane. And another condition is that it should have Euler product. Okay. So now let's see if this Hasse-Weil L function satisfies these 2 conditions. So second part is okay, right? By the construction of this. And this is not clear. Actually, this is the conjecture. It is by Hasse and Weil. This is called Hasse-Weil conjecture. Okay. And then later, Taniyama-Shimura conjecture is the following. So, okay. So let me rewrite this as a certain generating series. An over n to the s and so on to infinity. Okay? Then let me consider the following generating series. F S is infinity an times e to the 2 pi I n s. Here s is complex number. And Tarayama-Shimura conjecture is that this is then modular form of weight 2 and of level n. Now this is called modularity theorem. Okay, so any questions so far? Okay, so it means that for every modular form, we can also define the associated L function like this, because modular form has Fourier expansion, then the associated L function is of this form. So Fourier coefficient over n to the s. It means that the L function associated to any elliptic curve defined of Q is exactly the same as certain L function coming from modular form. This is called modularity theorem. Then why is this important?
When you talk about the level n, you specify the congruence of gamma 0.
Yes. So actually, gamma 0 n. Yeah. Okay. So why is this important application? So first application is that it is not difficult to show that any L function coming from modular form satisfies functional equation. So since this Hasselbeck L function is also L function coming from modular form, we already verified this Hasselbeck conjecture. So this is the first application, Hasselbeck conjecture. And second application is Feynman-Last theorem, as many of you already know about this. And third application is that under the assumption that elliptic curve has this modularity property, Gross and Saget found certain very interesting formula, which is called now Gross-Saget formula. Means that L prime E over Q squared root negative D and 1 H E P K. Okay, so I don't want to spend much time to explain what this is, but it means that this is a certain residue of L function associated to elliptic curve E, and this is actually Siegel point. This is certain geometric object, and Gross and Saget found this beautiful formula. Why this is beautiful is that this combined with Polyvagen's work, verifies certain very famous conjecture. It is BSD conjecture. Is true if analytic length of E is at most 1. Okay, so actually before the work of Mansoor Bhagavar about the average length of elliptic curves, this is the best theoretical evidence to support the BSD conjecture. This verifies the importance of this Gross-Saget formula. Okay.
What is the right hand side? H E of PK?
Okay, so actually this is Siegel point.
K is the imaginary quadratic extension.
Sorry. Yes, this is K. Okay, so for the definition of this Siegel point and this height, well, I don't quite remember it. Okay, but you can check. So, so you can check many references about this. Okay. So what I want to say is that modularity theorem is very important. So it means that if we have certain generating series, then it is very important to show that this is modular form. Okay. Later, Kodula vastly generalized this idea to the case of Shimura varieties. So X is G spin n minus 1 and 2 Shimura varieties. So on these Shimura varieties, he considered a certain very special cycle, which is defined as a certain moduli interpretation. And then he verified that certain generating series whose coefficients are special cycles is also modular form. Okay, so this part this work has actually long history starting from Kudla and Kudla-Milson and Rappaport. There are lots of work about that, and including Wei Zhang and Shou Zhang. Okay, but the remaining question and hard question is the following. Let me consider this. This is integral model over x defined over z, possibly away from beta prime 2. Okay. Then first problem is that, well, what is this integral model? It is not clear how to define integral model of this G-spin Shimura varieties because this is not of PEL type. So this is first problem, but this issue was solved by Kissin in 2010 in Journal of Ames paper. Okay. Now we know how to do that, but even it is very, very technical. Eventually, we want to show that certain generating series is modular. So it means that we need a very concrete model. Okay. Then in this case, this is Kudla's conjecture. Sorry, I think I'm very slow. So he considered certain cycles. Here B is N, Z. Okay, so B is n by n symmetric matrix whose coefficients are all integers. And then one can consider the associated cycles, and then its degree times Q to the B. His conjecture is this. This is the same as E prime tau 0 and C. Sorry. So this is actually the Siegel-Einstein series. Weight n plus 1 over 2 and degree n. Okay. So Kudla and Rappaport verified this only when n is 2 in his long and his series of papers with Rappaport and Tonghai Yang. Okay, but even in general case, it is not clear how we can define such special cycles. This is not quite precise. Okay, but this conjecture actually consists of two parts. So indeed, we can consider this as certain intersection number of several cycles. If we understand it like that, then the local version, so you know, intersection number consists of two parts. Intersection, the number of locals, and intersection multiplicity. The thing good here is that if I fix B, then in the associated cycles, each point has all the same ramification index. So intersection multiplicities are all equal. It means that this is, roughly speaking, the product of the local intersection multiplicity and the number of locals. So actually, to compute the number of locals, this is actually based on certain deep theory in ordering forms, arithmetic Siegel-based formula. And the calculation of the local intersection multiplicity is completely different from the number of locals. This follows from the size of certain deformation functor. Okay. So then local conjecture. Local version of this conjecture of Kudla is this. Now let me consider certain deformation functor of PW and BPX. Okay, so this is the category of certain. Okay, I first have to define what W is. W is the ring of bit vectors for FP bar. So we can roughly consider this as the maximum unramified extension of ZP. Okay? And then this is the category of all W algebras such that P is locally nilpotent.
Is it the P typical vectors or just
Pardon?
Or everything?
What is?
Do you consider the P typical bit vectors or all the big bit vectors?
Well, sorry, I don't know what P typical bit vector is. So, well, here, okay, so what so we want that this is the maximum unidentified extension of ZP.
Okay, that's a P typical.
Okay, thank you. Okay. So for example, here ZP mod P to the N ZP and then X, Y, Z. This is an object here, okay? And then BP. So here B is this N by N symmetry matrix, but it is well known that this cycle has support at only one prime P. So this is the P, and then this is the deformation function of X in the cycle. And then one can consider length. So Kudela's local conjecture is that this is almost the same as F BP 0 prime. So I didn't explain what this is. This is called the Siegel series. Okay, this is the connection between the topic of today's talk and this local conjecture of Kudela.
What does this IG mean?
What? Okay. So this is length. So
Length.
yeah. So well, if the dimension of this is 0, then it is known that this is actually represented by Artin local W ring. So it has finite length. Okay. In the general case, I don't know how to define this, but okay. Okay, so this is the motivation. So therefore, we really need a deep analysis about this Siegel series toward this modularity problem. Okay?
A similar conjecture among non-peltite Shimura variety exists.
Similar conjecture. Yes. So, okay, this actually G-spin Shimura variety is very difficult to analyze. But why they started from G-spin is that, well, actually, so to define G-spin group, we first have to start from certain quadratic space. The signature of this is n-1 and 2. Okay. Then we have then we have Siegel wave formula, so which gives relation between the orthogonal representation of orthogonal groups and orthogonal representation of symplectic groups. Okay. So this is a way to make a connection. This is a way to compute the number of locus here. The number of locus here really depends on certain set of theta functions associated to this. And then by theta lifting, this is now then related to the orthographic form of GSP, which is this Siegel-Einstein series. Okay. So the number of locus, well, the most difficult part here is to compute the size of the deformation functor and compare it with certain derivative of Siegel series. This is the most difficult part. Actually, recently, in 2010, Kudela and Rappaport started to study all these settings in unitary Shimura varieties, which is of PL type. And actually, one can also consider this for U and -1. Okay. In this case, they completely verified this relation only when n is 2, and their paper consists of their work consists of two papers. First, one major paper is to prove this conjecture, which is called the Kudela-Rappaport conjecture. And the second is to compute the number of locus by using Siegel wave formula, etc. Okay, so
That's what is BP? BP is some.
BP, okay, sorry. So B is n by n matrix. By saying BP, I mean B tensor with ZP. Okay, when this consists of finite points, then it is supported over F bar for fixed one single prime P. Okay. I think I can use this one. It's not good. So by the way, do you want to see the definition of Siegel-Einstein series precisely? If you want, I can write it down on the blackboard. Okay, then I will when I will explain, then it might be better to see why we consider the Siegel series. Okay, so here is definition. Siegel-Einstein series. This is usually denoted by E and K. So this is complex valued function whose domain is the product of upper half space of dimension n and c. Here, Hn. This is Siegel upper half space. So this consists of n by n symmetric matrices whose entries are complex numbers, and then we need more condition, right? So because this should be the generalization of upper half plane, so y is positive. It means that since y is also symmetric matrix, we can consider certain quadratic form associated with y, then this quadratic form is positive definite. Okay, and over degree n and weight k. So here nk comes from this degree and weight. So such that the pair of matrix NS maps to the following. 1 over, do I have enough space to write it down? I think I can use this. Okay, so let me write here. So the pair of matrix and complex number maps to the following sum. 1 over determinant, A, B, C, D, and comma n over n 0. C, Z plus D, K times determinant C, Z plus D, 92S times what? Determinant image of Z to the S. Okay, so here gamma n is sp2nz, and gamma n0 is a subgroup of this whose form is this 0d gamma n. Okay, so this seems to be not its definition, but let me state several properties of this Siegel-Einstein series. First, this is due to mass in 1971. So E and K. So because we have to be very careful because this is infinite series. So we have to first say when this is convergent. Okay? But so mass found that it has the Fourier expansion. Namely E and K ZS is of this one. Sum over C. Okay, B is symmetric matrix and n by n. The size of B is n by n. Maybe I think I can write down mn of Z. Okay, and coefficients depends on B and image of Z and S. And e to the pi I equals B Z. Okay. And then we found that this each Fourier coefficient has magnific continuation to all S. So it means that E and K has a meromorphic continuation to C with respect to the variable S. Okay. Therefore, to understand this Siegel-Einstein series, now due to this work, we only need to analyze these Fourier coefficients. Okay? But these Fourier coefficients had been well studied by many people from Shimura. So let me state another fact about these Fourier coefficients of Siegel-Einstein series. C, B, Z, S. Okay, so this is due to Shimura. 1982. He found that this is the product of two terms. First term is confluent hypergeometric function times another part, which is called Siegel series. Okay, and this part, and Shimura found a precise formula of this hypergeometric function, and this part actually involves the imaginary part of z, and then this does not involve imaginary part of z. So we can write it down as the following: b with b s, since it only depends on matrix b and s. So since this is completely analyzed by Shimura, now to understand the Fourier coefficient of Siegel-Einstein series, we only need to understand this Siegel series. Okay, but this Siegel series is actually different from the title involved in the Siegel series. And this is the first fact. And second fact is that this is not good because B is a global object. Okay, because local object is much better than this. And then Shimura also found that this has certain Euler product for all finite primes P. Local Siegel series. Now let me denote this by BP P P S. Okay. So now the notation of BP is that this is just localization of the matrix B with ZP. Okay. So then it means, so these two facts means that to analyze this Siegel-Einstein series, now then we only need to understand this local Siegel series. This is the topic of today's talk. Okay. Okay. So now let me move to the local situation. Okay, so indeed this local Siegel series had been studied by many people starting from Shimura and Kitaoka, and its precise formula was obtained by Katsurada in 1999. His paper was cited more than 100 times. But problem is that his paper and all known works to analyze certain properties and formula about this local Siegel series are not conceptual. It is not clear what their formula mean. Okay. So from now on, I will explain a conceptual reformulation of Siegel series by using another arithmetic geometry. Okay. So to do that, let me fix the notation. Even though I started from Z and certain matrix defined of ZP, this theory works for any extension of ZP, including 2. O and P. Pi is a uniformizer, and kappa is the latched field. And let's say that F is the order of kappa. Okay. And so here I use the matrix here because, well, it might be better to describe this Siegel-Einstein series. But since this is a symmetric matrix, I want something more canonical stuff. So it's better to work with quadratic lattice rather than matrix, because lattice is, independent from the choice of basis. Okay, so I will choose L Q is a quadratic O lattice. So, by the way, the definition of quadratic O lattice is that Q is quadratic form defined on L. So, or the associated matrix is symmetric and its entry is contained in O. Okay. Well, actually, its entry is contained in diagonal entries are contained in O, and non-diagonal entries are contained in 1 over 2 O. Right? Because what I need is that this is certain homogeneous quadratic polynomial defined on L whose values are in O. Okay. Okay, so there are many definitions to define Siegel series, but I like the following definition and most. So let's say that HK HK is certain quadratic lattice whose associative matrix is of this form, K copies. So this notation is not that bad. For example, if P is odd, then for any finite extension of ZP, then this 0, 1, 2, 1, 2, 0 is isometric to 0, 0, 1, 1, or this is isometric to 1, 1, 0, 0. Okay, over ZP, over any finite extension of ZP when P is not 2. So this is not big problem. Okay, then, so among all definitions, I like the following definition. Yeah, BP. So that's the definition of Siegel series and LS. So instead of using BP, now I will use L. So there is actually basically no difference between these two, right? Okay, so this is complex valued function, but if I evaluate this at certain integer, k is a certain integer. By the way, let me also fix n. N is the length of L. So it makes sense, right? Because I initially started that L is all lattice. So it means that free lattice with finite basis. Okay, so if k is bigger than or equal to 2n, then this is defined as the following: alpha p L HK. Okay, so this is called the local density between two different quadratic lattices. And what is the meaning of this? This is defined as the following: limit, okay, and maps to infinity f. F is the order of the latched field and negative n times dimension g. And what is g here? G is the set of all embeddings from L tensor with F HK tensor with F over F. So for example, if we take L as HK, then this is nothing but the orthogonal group defined over local field. Okay, so this represents the set of all isometries from L to HK over field. So this is not orthogonal group, but this looks like orthogonal group. But actually, by Witt theorem, you know that this is more or less orthogonal group. This is principal homogeneous space, quotient by OF, and L tensor F is dual inside HK, inside the quadratic space spanned by HK. So what does that mean? It means that we know the dimension of this, right? Because so since HK is defined as this, the dimension of this as a vector space is 2k. So dimension of this is 2k times 2k minus 1 divided by 2. This is very well known. And this, what is the dimension of this? Since n is the length of L, the dimension of this is also n. Okay? So then we know the dimension of this precisely, so this part is not problem. Okay. Now, then the remaining term is actually very annoying part. This is the order of O L quotient by pi to the n L HK quotient by pi to the n L HK, sorry. Okay. Over O mod pi to the n. Okay. So it is known that this limit stabilizes when n is big enough. So all traditional work to compute and to study certain properties of a Siegel series is to analyze this limit. On the other hand, so the starting point to connect this with arithmetic geometry is this. Just in case this is smooth, this is where okay, so remark. On the other hand, I can consider LHK. This is the set of all embeddings from L to HK as all lattice. Okay? But it is clear that this is actually a affine scheme defined over O, because all equations defining these are polynomials. Right? So this is obtained by one single matrix equation. So this is affine scheme. So just in case this is smooth affine scheme defined over O, then this limit stabilizes at the very initial step when n is 1. It means that then this. So when n is 1, then what is this? This is the order of the special 5 of this, right? But sadly, this is not the case happened in almost all cases. This is smooth only when L is the same as HK and P is not 2. Okay, so in almost all cases, this is not happened. And let me BP first remark, second remark, alpha P, L, HK. Okay. So let me give you another definition to define, to give this. So, okay. Now, let me consider this as a set over O. Okay? Then this is P-adding manifold. Then we can just consider certain volume form associated to this. Then this limit is nothing but the volume of this with a certain natural volume form. Okay. So my starting point is to analyze this integral. Okay. To do that, I think I can erase this. I think I want to keep this. Okay. Maybe I can erase. Okay, so I will use this definition for the Siegel series. Okay, so I said that in the most cases, this is not smooth over O. So I will define certain subset of this. O primitive. LHK. This is not that bad. This is the defined of all isometries from L to HK. OO, L, HK. So let's just consider this as a set. Okay. Later we will impose a certain scheme structure here, such that F modulo pi is injective. So what does that mean? Let me give you one example. For example, so to simplify notation, assume that P is not 2. Then let me consider H2. H2 is isometric to one identity matrix. Okay. Now let's say that my matrix, my coordinate lattice L is given by this matrix. F11. Wait. I need 1, 1, 0, sorry. 1, 1. Symmetry matrix. 0, 0. Okay, so I think this is not good choice to choose matrix. P. 0, 1, P square, 0. Okay, then. Oh, sorry. I think this is not a good example. So, okay. So assume that my lattice is given by this symmetric matrix, and let me consider another lattice given by 1, 1, 1, P square. Okay, this is not H2, but so I just want to show you one example why this is strictly smaller than this. Okay, so let me choose 4 bases: E1, E2, E3, and E4. And here, E and E prime are bases of this lattice. Then, if I choose isometry so that E maps to E1 and E prime maps to E4, then this is isometry, right? So this preserves the associated quadratic forms. And furthermore, pi modular this modular maximal ideal P pi is also injective Okay, so this is injective. But what if this E maps to E1 and E prime maps to PE2? This is also isometry, right? But psi modulo P or maximal ideal is not injective because E prime maps to 0. Okay, so what I want is that I want something like this. Okay, then what we can see is that if you see this example from psi, then I can consider the following. So L is now spanned by E and E prime. Then I can consider a certain lattice slightly from L prime, which is spanned by E and 1 over P E prime. Okay, now then, the symmetry matrix associated to L prime is this 1, 1, 0, 0, 1, right? And for this, then this psi naturally induces isometry from L prime to, I have many L prime, L tilde. From L tilde to L prime, then its mod P reduction is now injective. Okay, so it means that we can get certain stratification about this set in terms of this primitive certain isometry sets. Okay? So using this idea, now OOLHK as just a set as a set of isometries from lattice L to HK. It has the following stratification: OO primitive and L prime HK, where L prime is certain quadratic lattice including L and integral, and both have the same length, such as this. Okay, and fact is that this is a finitely disjoint union. Okay, and this is the first remark. Second remark. Now let's consider OO primitive LHK. So what is the condition defining this? So the only condition defining this as a subset of this is that at least one n by n minor is invertible. Right? It means that this is actually subset, open subset of this. This is open subset as p-adic topology. Okay. So and furthermore, since the only conditions defining this as a subset of this is that at least one n by n minor is invertible, it means that this is also open as subscheme. Right? But this is not affine, but this is like finite union of affine schemes. Okay. Now then, let's recall the definition of this Siegel series. I said that this is defined as a certain volume form of OOLHK. O point. Okay. Since now I have certain stratification of this set, I can rewrite as the following. Since this is this disjoint union and each set here is open in terms of p-adic topology, I can write this as following. OO L prime primitive HK O and WL LD. Okay, so this is just trivial, right? But this is not that good because so I have certain volume form associated to L, but this is a set associated to L prime. So I have to replace this by L prime. Okay, we can do that because this is actually open subscheme of this. And furthermore, these two have a finite index. We can precisely check the difference between two volume forms about L and L prime. Then it is this F to the n plus 1 minus 2k. Okay, so F is the order of the latched field, and this is just the index. Okay. Okay. Now the first theorem is this. Now instead of working with this, I will observe this another scheme, OO primitive and LHK. So obviously this is certain non-affine scheme defined over O, but this is smooth, defined over O. Okay. So actually, this is non-trivial data. We have to prove this. Okay. Why is this important? At the beginning of this talk, I said that if one certain scheme is smooth, then its integral is almost the same as the order of the special fiber of this. It means that its corollary is the following. This integral, or primitive, LHK, and WL prime. Yeah. This is now nothing but the order of the special fiber of this, or kappa L mod pi L HK mod pi HK. Well, actually, I have to multiply the dimension of the genetic fiber of this, but yeah, this is not bad. Okay. So then, what is this? This is the set of all isometries from quadratic space to another quadratic space defined over finite field. But you have to be very careful. This can be highly degenerate. Okay. For example, okay, in this case, L mod pi consists of 1, 0, 0, 0. Okay, this is degenerate. Okay, but it doesn't matter. So the order of this set is very well known. So fact is this: the order of this O kappa L mod pi HK mod pi. So this is very well known, but I don't want to write it down on the blackboard. But I found that this depends on the following. This depends on the following invariance of these two quadratic spaces. First of all, it should depend on the dimension of this. What is the dimension of this? The length of HK is 2K. So dimension of this is 2K. Okay? So and the second, the dimension of this is n. Of course, because L is the length of L is m. Then A. What is A? A is the dimension of non-singular part of this. Okay? So for example, in this case, L mod pi L is 1, 0, 0, 0. So A is 1. Okay? But actually, I have to assign plus minus here. So for example, if A is plus, then if A is odd, then all non-singular quadratic space of odd dimension are all equal isometry. If A is even, then there are two cases, split or non-split. Anyway, so this is not big deal. Okay. So now then I can rewrite this by the following invariance, A and 2K. But N and 2K are already fixed from the initial step. Right? So it means that now then, okay, now we are almost all done. LHK. So this is the definition of Siegel series, then this. This is the sum for all quadratic lattice, including L, and then each summand is this, F to the L prime L something times the order of A and 2K. Okay, but this sum is also not good because we don't know how to handle this, the set of all lattices. So, but if you see this summand, then we can find something very interesting. So, for example, let me choose two lattices, including L, satisfying the two conditions. Okay, so A plus minus associated to L prime mod pi to the L prime is the same as A plus minus associated to L prime L double prime. So they have same A. And second condition is that the degree of L prime over L is the same as the degree of L double prime over L. Assume that L prime and L double prime satisfy these two conditions. Then what is happening here? For such L prime and L double prime, this each directs, each summand are all equal, right? Because each summand depends only on two invariants of L prime. One is A, the other is degree here, right? So for L prime and L double prime, these are equal. Therefore, it is now then reasonable to consider the following set. I will define the following set. This is the set of all lattices including L satisfying two conditions. First condition is this, L prime L is fixed by B. B is the integer. I fix this. And second condition is that dimension of L mod pi to the L, dimension of non-singular part, is A plus minus. Okay. Then if I choose two lattices here, then their contribution in the sum is exactly the same, right? Okay, then in this way, I can write this trivial series using the cardinality of this set. Okay. Then using this, alpha LHK is this f to the negative 2kn plus n plus over 2. So this is not bad because we know everything here, f kn times sum a and b about a and b, the order of s l a plus minus b hide this. Okay. And then f to the n plus 1 minus 2k, that the order of O kappa a plus minus n 2k. So as I said, this is very well known. Okay. So any question? So now the fact is this. Alpha LHK. This is actually polynomial about f to the negative k. Okay. Right. Okay. So for example, if I denote this by x, then this part involves x to the 2n, and this is certain constant, and this contains x square, and this contains, so this is completely expressed in terms of certain polynomial about x, because we already know this very well. Okay. So it means that, so, okay, this is first fact and second fact. BPLS. So this was the Siegel series, and I said that when S is K, which is bigger than 2n, then this is defined as this, okay? So it means that if I denote this by X, then alpha LHK. This is certain polynomial about X, right? Okay, so it means that this is now, we can also write it down as polynomial with respect to certain q to the certain f to the negative s. Okay, so now then it means that then this. So since this Siegel series is polynomial, this Siegel series is now then completely determined by its coefficients. Now this reformulation gives us a conceptual interpretation of each coefficients. This is a certain like weighted sum of certain lattice counting argument. Okay. So then why is this important? So then remaining question is, so what? Why is it so useful to Kudela's program? So now this is another theorem. Okay. So okay, then you can see that this is already very well known. This is very classical terminology. So to understand this, we only understand this, the set of certain lattices satisfying A-B condition. I very precisely studied this set, and then I found a certain inductive formula about the set of certain lattices. Then I obtained the following inductive formula. So let me denote this polynomial by FLX. Okay, so because I said that this is actually polynomial about x. So FLX. This satisfies the following inductive formula. And D, okay, Cm f to the n plus 1. Actually, I wanted to show this on the project, but project didn't work. X to the.
Maybe it's still possible.
Huh?
Maybe it's correct. It's still possible. But
Yeah.
do you want to?
Yes. I think if we can use this, then yeah, that might save our time.
It might take some time.
Okay, then. Okay. Maybe.
16, 15.
Okay, that's not bad. Okay, then I can save my labor. Maybe I can erase this. Okay, so how can I? 전체 보면. Okay, so this is the inductive formula I obtained by analyzing this set. Okay, so there are many ingredients here. So basic idea is this. So assume that P is not 2, but actually this formula works in in many cases. This formula works for all R prime P, and when P is 2, this formula also works for anisotropic quadratic lattice over Z2. Okay, but Cordon program involves only these two cases, R prime and anisotropic over Z2. So this is okay. So if P is not 2, then L. We can diagonalize this like this. P to the A1, P to the AN. So for any R prime P. And then, so let me, okay, A1. Let me write this exponent as n tuples here. Okay. So, and such that A1 is, A2 is bigger than or equal to A1, and so this n tuple satisfies this relation. Okay. So it means that then we can at some point find D, n minus D, such that the next an minus D plus the next one is all equal to the same as an. So D is this D. So it means that D is the number of the multiplicity of an, the biggest integer here. Okay, this is D, and this is Grassmannian about n-dimensional vector space to choose d-dimensional vector space, and this is the order of the Grassmannians. Okay, so this is the inductive formula. Then, why is it useful? And I found that, so initially I said certain Cordon's conjecture in all known cases, this formula is actually exactly the same as a certain hidden formula in Cordon's program, in Cordon's local conjecture. Okay. Okay, so this is the ingredient in the use to the proof of this theorem. So stratification of P-addict manifold, and each straight term, you could see that each straight term is smooth defined over O, so that we could conceptually analyze it in terms of certain few invariants, and it also involves Grassmannian and lattice counting argument over there. Okay, so I think that, so actually I started from quadratic lattice, but I think that I checked all crucial stats, but it seems my formula works even in the case of Hermitian forms. But this is very good. Initially, Cordon conjecture is very difficult for quadratic forms, but if we work with Hermitian forms, then we can manage this, because then the associated Shimura varieties and the associated deformation problem is very well described in terms of certain Laborde zinc space or PL type. Okay, so now so this is Kudlar-Laporte conjecture. This Kudlar-Laporte conjecture is just the Hermitian version of the local conjecture by Kudlar to give matching between so the intersection multiplicity and so the derivative of this trivial series. And Kudlar and Laporte also expected this relation holds in Hermitian forms case, in unitary group case. And I and Wei Zhang made the following conjecture. So how I could get this is that, so I said this formula, so in all known cases, this formula is the same as the formula used in the calculation in Kudlar's program. Okay, so it means that in unknown cases, if Kudlar's conjecture is true, then this local intersection multiplicity also should satisfy the inductive formula coming from this. So that's how we could make this conjecture. Okay, so I'm now working to prove this. If this, so also this is the first known theoretical and conjectural relation about this. Okay, I will stop here. Thank you very much.